So today we're going to continue with directed graphs and introduce what's called a network. So this is a further sort of graph model. I'm going to prove a key theorem here, which is one of the 6 theorems: Hall's theorem, Menger's theorem, Koenig-Egger-Vari, and today we'll learn the Ford-Fulkerson theorem. So all 4 of these are equivalent to each other. Okay, so what is a network? So a network is a directed graph, D, with a couple of special things. So there's a source and a sink vertex, and then there's something called a capacity function. Okay, so directed graph together with a source, vertex S, which is just a vertex of the digraph, and sink vertex T. So they're just specially identified vertices of the digraph that are going to have special properties, and a what's called capacity function. On the edge set. So a capacity function is just a weight function. It's an assignment of a real value, typically a positive real value. In fact, I'll say positive real value assigned to each edge, each arc of the digraph. Okay. So let's say, how about this? Let's say non-negative. Okay, non-negative reals here. You can allow negatives as well, but you'll see how this is just there's no real purpose to this. Because it's a directed graph and we have directions on the edges. Okay, so let's draw an example here. It's very simple, and we'll work with this example a little bit more. That's our source vertex, and let's say the graph looks like this. The digraph looks like this. Here's our sink. Let's say there's an arc here as well, and maybe let's have like a second arc here in the reverse direction. Okay, and let's say the arcs are oriented as follows. Let me draw that a little better. 2 arcs are going out from S. Maybe this one's going down here. Back, forward. And then this one goes into T, out of T. And then this one goes up. Okay, so here's our digraph, and then each edge is assigned a positive real. I'm just going to use integers here. So the capacity function is 1 there, 5 here, 3 on this edge arc. Let me give a little some more space here. 3, and then 6, 2 on this arc, 1 up here. Let's say 2 here. Let's also make this one 2, and then 4 and 5. Okay, so this is a network. The weights that I've assigned to each of the edges are the values of this capacity function. Okay, those are the things there. Okay, so what we're interested in a network is what's called a network flow. So what I'm going to try to do here is really think of this as like, I like to think of this as maybe like a water network. And each of these capacities is a pipe that runs in one direction and can have this much water flowing through it. 1 gallon can flow through this pipe per minute or something. This is a bigger pipe, can do 5. This can do 3 in this direction, 6 this way, and so on and so forth. And what I'd like to do is send the most water per minute from S to T, right? And just if you like look at this picture and try to make some really simple observations, obviously the most you can send out of S is 6 per second, right? That's the 2 outgoing there. But that doesn't mean that the rest of the network can support that. Maybe there's a bottleneck where you have a vertex that can only have 2 liters per second, 2 gallons per second coming through it. So then I wouldn't be able to send 6 out of here because there'd be a bottleneck somewhere else. In this specific example, we are able to send 6. If you examine it, you'll see. But we want to model this as some kind of graph theory problem, some sort of algorithm to figure these things out, to figure out what the max is. Okay, so that'll be what a flow is, which I'll define in a moment. It's another function obeying some properties. But I think the easiest way to visualize this is some sort of water network. Any kind of network works fine, though, of course. Okay, so I'm going to put this in red. So a flow in network D. Okay, so slight abuse of notation. A network is not just a digraph. It's a digraph with two special vertices and a capacity function. But usually when we talk about a network, we just refer to the associated digraph. But keep in mind, like very formally, you know, what is a network? It's a quadruple, right? It's DSTC, right? It's a digraph with two special vertices and a capacity function. But I mean, you're never going to refer to it this way. Okay, so a flow is another function. So a function, again, from the arc set of the digraph to the positive reals or non-negative reals, such that two properties are satisfied. Okay, so the two properties, let me put them in words first. The two properties are that the flow on any one edge should not exceed the capacity function along that arc, right? You can't have more water passing through a pipe than that pipe allows. The other rule is that if I look at a vertex, the water flowing in should equal the water flowing out. Very natural restriction, right? The total sum of the flow going out is equal to the total sum of the flow going in. Like water doesn't vanish from my system, okay? Except for at the source and sink. That rule doesn't need to be obeyed at the source and sink. The outflow and inflow at the source and sink, there's no inflow to the sink. Actually, you can put inflow and inflow to the sink, but the point is the rule of the sum of in minus the sum of out doesn't need to be obeyed at those, because at the beginning and end of the network, there indeed the water is, you know, vanishing, right? It's pouring out of your pipe system into a trough or something like that. Okay, so the two rules are one. So the first one we call, this is the capacity rule. CR. And this just says that for every edge, every arc XY, we have the following, that the flow on arc XY is bounded above by the capacity of XY, right? You don't have more water flowing through there, and it should be positive. We stated this thing here so that the flow was a non-negative integer anyway, so this lower bound here is automatic. Yeah. Like you don't like, if you wanted flow to go in the reverse direction, it would be better to actually put a pipe going in the reverse direction. Like in principle, you can talk about negative flows here along an arc here, but that's the same thing as saying you have a flow in the reverse direction of a reverse oriented arc. And you can model it that way. Those things do work, but I don't think that helps us. Okay. And then the second rule is Kirchhoff's law. Kirchhoff's law. Anybody seen that before? That appears in a totally different discipline, right? This is from like electrical engineering, right? It's like I don't know exactly what it has to do with the voltage into a circuit is the same as out or something like along those lines, right? Yeah. So, and this is the same thing obeyed here, right? The flow into a point is the same as the flow out of the point. Okay, so for every vertex in the network, excluding S and T, right? S and T are not bound by these rules. We have the following, that the flow into X, actually, is the flow into X? Okay, yeah, let me, the flow into X, so that's the flow on each arc YX. X is fixed, right? And so I sum up over every arc YX, that's an arc. So that's the sum of the flows going into X. So sum flow into X should be equal to the sum of the flow going out from X. So that'd be XY, sorry, XY is an arc. Okay, so those two sums should be equal to each other. That's Kirchhoff's law. Okay, so any real valued function on the edge set, the arc set of D is a flow if it satisfies these two rules simultaneously. Okay, so there are many different flows potential. For instance, if I just assigned 0 to every single arc, in this network here, then that would be a legitimate flow, because of course it immediately satisfies this and this. All right. So I did this in red because I want to write a flow in this network as well. Okay. So I'm gonna write one down, but I'm gonna like, you know, guess here, like see if I can make it to work. But like, you know, in principle, if you just start writing down flow values, like it's not easy to guarantee that your two flow conditions will be satisfied like at the end, right? You have to check every vertex, but in a like a hand example, it's not too hard. Okay, so in red, I'm just gonna write it down like this. Okay, so this means that I have flow 1 traveling along that arc. It's at least 1, and I mean, it's at least 0 and it's a most 1. So at least on this arc so far, the capacity rule is clearly satisfied. Kirchhoff's law is not satisfied at all, but we should check Kirchhoff's law after we've identified the entire flow. Okay. Let's also have 5 going out from here. Okay. So this was the max we could ever hope for, but let's see what happens here. Okay. Let's continue to have 1 along this arc here. I'm going to have 0 going down here. So no flow goes down on this pipe here. So this pipe is not used here. And then along this pipe, I have 5 traveling. It continues from here. Okay, and then, oh, by the way, there's a mistake in the picture here. This arc should be oriented into T. Oh, I want to do that in black. All right. Okay, let's continue building a flow. This 1, let's have it just, well, I don't want to do that yet. So this 5, it reaches this point here. And obviously I want this 5 to travel into T, like I'm hoping for it to get into T. But once I've reached here, I can't have 5 go along this arc because the capacity is 4. But let's fill up that. That's a reasonable thing to do and make it fill up. And then the remainder of this has a couple of options. There's one more value of flow that has to leave this point here in order to satisfy Kirchhoff's. I can go along this arc or I can go along this arc. If I go along this arc, I'm going to run into trouble because I'll either go here and have to get out some way, and that's already at capacity, or I could go back down here. But then if I have flow like travel back around here, like there's capacity issues as well. I mean, you can probably predict that this is not going to have any chance, right, of working. Okay, so I'm going to send that continue to send flow up here, and then they reach here, and then fortunately this capacity is 2, so it can absorb the capacity from this incoming. I mean, the flow from this incoming edge and this incoming edge, and so this is at most 2, and that goes into T. Anything else I haven't used, is just 0. Okay, so this is 0 as well. Okay, so this is a flow. I mean, we didn't check Kirchhoff's, but maybe we can check it real quick here. So certainly the capacity rule satisfied everywhere. The way we built it up, we were always below the flow, at most the flow. And then Kirchhoff says, okay, for every vertex other than the source and sink, do the sum of incoming and outgoing match each other? And it's easy, but let's like look at a couple real quick anyway. So this vertex here had 5 coming in from here and 5 going out from there and 0 coming in from here. So in plus out, in minus out was equal. Up here, 1 in, 1 out, no problem. This vertex was a little more interesting. It had 5 in, but then 1 out, 4 out. So that adds up as well. And then up here, we had one at this one here, 1 in and 1 in, and then 2 out. Okay, so actually now we actually checked all the vertices. So everything satisfies Kirchhoff's. Again, the source and sink we didn't check, but those don't satisfy each other. But what about the inflow to T and outflow from S? How are they related? At least in this picture here. Right, like if I went and said compute the inflow, yeah, they're equal, exactly, Max, right? The inflow to T is the same as the outflow from S. I mean, that's just sort of like evident. Like from a metaphoric point of view in this water network, it makes sense, right? These rules made it so that none of the water vanished. So it has no choice but to end up in T if it started from S, if all the other rules were obeyed, okay? And actually, we're gonna confirm that in a moment in general, right? But that, I think, like it literally follows from the Kirchhoff law here. Okay, all right, so then we have this lemma. And this lemma is, I'm going to call, the name of this lemma is going to be the flow value. Okay, so we can assign like a value to this flow. And that's just the value of the following here. Okay, so let D be a network with flow F. Okay, so we have a network and it has a flow F. And remember, a network has a source vertex S and a sink vertex T and a capacity function. Actually, the capacity function doesn't come into this. Okay, so then the net flow into S, sorry, equals the net flow out of T. So the net flow into, no, that's backwards, of course. Net flow out of, yeah, let me, this is exactly the reverse of what I want. So the net flow into the source sink is equal to the net flow out of the source here. So what's net flow? That's the sum. So the net flow out of S, like what does this actually mean, to be precise here? Well, okay, I'll write it down in an equation in a moment here, but what the net flow out of S means, it's the sum of all the flows exiting S minus the flows entering S. It's possible to have flow entering the source. Usually it's redundant and you don't need to have it, but it, like, for instance, okay, we didn't see it here, but in principle, I could have had flow on this edge here, leaving the sink. Okay, obviously somehow that sort of has to get back into there at the end by these rules. But when I do actually compute, I need to add up incoming and subtract outgoing for T. That would be the net in to T. And the net out of S would be all the out ones plus potentially the in ones there, minus the in ones, sorry. Okay. So what this says, just if I write it out, is that, so I said net flow into T. So let's say the value that's usually going to matter here is xt, so the flow xt, where xt is an arc, minus the flow out of T, which usually won't be there, but could be. Tx is an arc. And this equals something similar for the source. So for the source, it should be Sx, which is outgoing from the source, the flow. So Sx is an arc minus anything that potentially goes in. Xs. Xs is an arc. Okay. So the lemma claims that this left-hand side equals the right-hand side, or in other words, the net flow into T equals the net flow out of S. Okay. This doesn't hold for the capacity, right? The capacity function could be like whatever. Those are just bounds on the max flow you can have. The capacity out of S has nothing directly related to the capacity into T. Actually, in this example, they're not equal, right? The capacity here is 6 going out, but the capacity into T is 4 plus 2 minus 2, right? Even, I mean, I could ignore this one, but it is there, right? Capacity is nothing. And moreover, like, say I change this 2 to a 200, then the capacity would be way different. But actually, I wouldn't have been able to like increase the flow here. Like, I mean, you just have to check the example. Okay, so this is the lemma. We're going to prove it in a second here. But this value that's computed here, this is called the value of the flow. Okay, that's like how much is going out of the source and ending up in the sink. So that's like how good that's how much water, right? That's just how much water. Okay, so either they're equivalent. I mean, they're equal to each other. But let's say this is the value. So this is a definition of the flow F, and it's denoted V of F. Okay, so now we have a thing we can record how big a flow is, right? And of course, we want to maximize this, right? We have some network of pipes here. I want to know what's the best I can do. What's the most water I can send across at any given time? Okay, let's prove the lemma first, though. Okay, so Kirchhoff's law is obeyed at each vertex of the digraph except for the source and sink. So I can do the following. I can just sum up the value of the flow into a vertex X minus the value of the flow out of that vertex X, and that equals 0 every single time. So if I sum over every vertex of the digraph other than S and T, then the result of this computation here is every term in this sum will be 0. Okay, let me write it out a little differently. So, no. Okay, so sum up over every and then I compute the following sum. I'm going to compute the flow into X and subtract from it the flow out of X. Okay, so every arc YX. So keep in mind, when I'm computing this sum here, X is fixed, right? For every vertex, check all the incoming edges to X, compute their flow, YX, and then subtract from that for every arc exiting E, the flow of that arc. Okay, this whole thing should be equal to 0. And that's simple just because like every term in this outer sum is 0, right? Like this equals 0 by Kirchhoff's law, right? Kirchhoff's law says that the inflow equals the outflow, has to be. Okay, so if I subtract them from each other, I get 0. So this equals 0 and I take a sum of a bunch of zeros. But now I want to recompute this in another way. Okay, so observe the following. At least when an arc doesn't involve S or T, so if arc, say XY, does not use S or T, then the XY appears twice in expanded sum, right? So if I wrote out all the terms of the sum before canceling, so over every single vertex that was other than S and T, I computed all of these flow values before subtracting from each other. For any given arc, like this, XY, the flow on XY is going to appear exactly twice in this expanded sum, right? On one occasion, it will be computed here, here, because this will be part of the flow out of X. And in another occasion, it'll be the flow into Y. So maybe it's even, well, I don't want to change it, but maybe you'd be better to call it X and X prime or something like that, right? I mean, but nonetheless, this arc will appear in a positive part in one part and a negative part in another part. Does that make sense? Everybody there? Like if you just write the thing out and expand, I mean, this is like handshaking lemma in disguise. Each arc has a starting and an ending vertex. And at some point I compute the flow out of X. And so this term appears. And actually, so the flow out, so it's negative when I compute it out of X, right? That's how I did it here. And when I compute into Y, it'll be here. It'll be the in. I mean, like Y is part of the index here. This is a fixed Y. Like I hope that's okay for you guys. Like this is not uncommon in mathematics, but it is easy to confuse the two there. Okay. But that doesn't hold when S and T is involved. When S and T is involved, like think about S and T for a second. When I have S here, it has a bunch of arcs on it, but these arcs will not appear twice in the list here because I don't take the sum over S. So the arcs out of S and into S will only appear once in this term, this thing here. Now everything still cancels and I'm left with 0. But if I cancel terms by like looking for identical arcs, those cancel with each other. So I want to look at what's left over at the end here. If I do it that way. So I can't, so let's say cancel these. And we have what I'm going to write here left over, which will be equal to 0. Okay. It's very easy to mess this part up. And I think in my notes, it's flipped from what I want. So I updated it a little bit. So let's look at the S arcs here. Okay. So if I have S here, then all the arcs leaving S will appear in this type, right? So this is S, and each of these could be an X. And when I grab an X, I compute the flow into X, and there are X's for which it receives flow from S, and those are not. There's no. I will never compute. Never over here will never appear the term X. The incoming flow. So the outgoing flow from S, right? Because S is not a part of the summation here. So these will be left over. I'll have F SX X. So SX is an arc. Those will be left over. And also we will have the flow values into S, but those will be subtracted because those will appear here when, did I flip this around? I think I might have flipped it around. SX, no, I'm okay. XS, and this is XS is an arc. Okay. But we have something similar for the t's as well, right? For the t's, I will compute all of the flow from t to x. So that's outgoing flow from t, just like this guy here, right? At some point, this y is s, and at some other point, this y is t, right? Remember, y is the chain, x is fixed, and it's not s or t. Y is every other potential vertex there. So sometimes s appears there, sometimes t appears there. So tx is an arc, and then minus the flow of xt over the appropriate arcs. Xt is an arc. Okay.
Hey, Corey, none of us can hear you.
How about now? Can you guys hear me? Okay. Yeah, I don't know.
Yeah.
I have a desk mic here, and yeah, that was weird. Let me continue with this. Okay, so where was I? Oh yeah. So if we rearrange terms and bring, I don't remember which one, maybe bring this guy to the left-hand side. Let's just double check if this matches well, I mean, actually we can just read it out, what it should say. This here is the net flow out of S, right? S out to X minus into S. So this is net in to S. And then this thing here, when I move it over to the left-hand side, will be the net flow. This is the negative of the net flow out of T, sorry, into T. Geez. This is net flow, net out of S, right? Out of S minus into S. That's the net flow out. And this here is the negative of net into T. But when I bring it over to there, it'll be the net into T. And so the two equal each other, okay? So this is just to confirm what we kind of already could see pretty easily from the previous example, that anything leaving S ultimately terminates in T and has no choice. I mean, in fact, that basically is the proof, right? At each vertex, the net flow out, the out is the same as the in, except for S and T. That flow has to go somewhere, so it ends up in T after starting from S. Okay, this is just a computational way of doing it from the Kirchhoff law. Okay, and so now it's justified to use the term value of a flow. The value of the flow is that fixed quantity leaving S, net leaving S, or net entering T. But those only, right? At any other point in the flow, like the net flow in and out of a point is equal, but it's not equal to the largest flow in that, like, right? So this is the value, right? Okay, so now go back up to the example here and think about like some way of deciding how big we could make this flow. So does anybody see, just looking at this picture, one like upper bound on the flow, like one sort of trivial bound that says there's no way we'll have more flow than that? Yeah, exactly. Eric says 6, and Eric, where'd you get 6 from? Just to illustrate.
Because you can only get 6 going into T.
Yeah, exactly, right? The best we could hope for into T is 6, right? If those capacities were reached, they can't be exceeded. Another one you could also look over here, and this is a coincidence, but there's 6 coming out of S as well. You'll never exceed that as well. But there are other possible, bottlenecks in this network. I mean, this is not a good example because the maximum is 6. But maybe just like let's make a real baby example here. So say you have something like S and T, and the flows are 100, 10, and 1, right? Well, obviously the flow is not going to exceed 1 here. Kirchhoff's law is obeyed everywhere, and this, you have like a literal bottleneck here, okay? And so we want to figure out like where that bottleneck is, because it doesn't have to be at the source or sink necessarily. And then what we'll find out is whatever that bottleneck is, how we define it, that will actually, you can achieve a flow that hits that makes the bottleneck stuck, okay? The proof is not very difficult, but there's some other interesting like related issues that will come up. Maybe I'll state them at the end here. Okay, so that's what we're going to try and prove here, and that's the max flow min cut theorem. Okay, but we need one more definition in order to do that. So we need to measure somehow the bottleneck, like the flow that you can have across some barrier here. Because in that simple example I showed, it was obvious 1 was the barrier, but what if you have like a really complicated graph? How do you know like what's the barrier here? Okay, so we'll call this a cut. So a cut in network D is a vertex partition ST. So I split up all the vertices into 2 classes, S and T, with the simple property that S contains the source and T contains the sink. And the other vertices are just distributed among them, actually any way is possible, okay? So such that S is in S and T is in T, that's it. There's tons of partitions of the vertices, and most, I don't know, most, whatever, some of them have this arrangement where S is in S and T is in T. That is a cut. It's as simple as that. So it usually looks like this. We usually draw it like, here's the source and here's partition class S, and here's T, and this is set T. And I mean, yeah, okay, so like this illustration is maybe not completely accurate because it kind of suggests that these are components or something like that. It doesn't have to be that way. In practice, that is what matters, but it doesn't, I'm not saying that these are like reachable from S. Although we should assume that the network is like connected. Anything that's not connected to my source like is not going to be relevant at all, right? So S and T should have a path, and anyway. Okay, so this is a cut, very simple cut. And then I want to look here at the capacities. Maybe I shouldn't do that in red since red's always been associated with flows. So we've got some arcs like crossing over here, right? And I'm going to draw, it's possible to have an arc in the reverse direction too, but this doesn't come into it. It's not going to be important. So let's look at this network here. Like, based on this picture, is there something you can tell me about the maximum possible value of a flow based on like this picture here, like in terms of bottlenecks? Like what these forward edges, what's important about their capacities in terms of ultimately finding a flow? So certainly no flow, yeah. Yes, exactly, Ethan. So a potential flow can't exceed the capacities on these forward going edges, right? Just think about, you've got some flow exiting from S, and it goes wherever, and then it's got to get to T somehow. So this partition class has T, and so somehow it has to cross the barrier from S to T somehow. Well, the maximum flow that you can get over to this side from this side is just if all these capacities were reached. That may not be possible, but you can't have more than that, right? You certainly can't have more than that. And any capacity that does get across, what happens to that? I mean, any flow that does get across, what can you tell me about that? At best, that all ends up in T, right? Actually, some of it could go back along one of these edges, but I'm just talking about an upper bound, right? So a value of a flow can't exceed what we call the capacity of this cut here. Okay. So the capacity of a cut ST, so just that special partition, is, so it's just CST. That's how we denote it there. That's the capacity. And it just equals the sum of all the edges going from S to T. We don't subtract the backward edges because those, you might have no flow going along those. So they don't contribute to an upper bound. Okay, so let's say X is in S, Y is in T, and we just compute the capacity of arc X. How do we define, the capacity function was on an arc, okay. Okay, so to be strict here, formal, X, Y should be an arc as well, right? If I grab a vertex here and a vertex here and there's no arc between them, then there's no capacity function associated. But if you want to avoid this, you can just pretend that capacity is 0 on arcs that weren't drawn there. In fact, some people will talk about a network as being a complete digraph where all edges are available, and if you want an edge not to be used in your not to exist, you just assign capacity 0 to it, right? It's the same thing. Illustrating that's stupid though, right? I mean, like if you have no capacity on the arc, just don't draw it. So it's better to do this. So I usually won't write this extra term though here. So we'll just keep in mind that if there's a non-arc, then there's no capacity. Okay, and so we just observed that the value of a flow, of any flow, but even the best flow, is never going to exceed the capacity of a cut, ST, no matter what cut we choose. Okay, and actually the easy, yeah, Van, exactly. So we've talked about an ST separator when we, or actually I don't know if we talked about it. Maybe it only came up in like we ran out of time and it was in one of Menger's theorems. But it's the same thing. The only difference is it's a separator. So it's just defined in a slightly different way because it's not a set of vertices that separate X from Y. It's actually produces a set of edges that separate S from T, and it's in a directed graph, so it's a little bit different. It removes all potential ST edges. But actually, Van, it's a good question because Menger's theorem follows in like 2 lines from the network flow theorem when I state it in a moment here. You just have to take your graph, direct it, make the appropriate capacities, and then figure this stuff out. And it actually, like, I mean, it'll be a homework, so you guys will see. Yeah. Okay, so this guy always holds for any flow and for any cut. And the early observations that we made a moment ago about this, the flow, the capacity coming out of S and the capacity going into T as upper bounds on the flow, those are captured by this observation, because those are just the very, very simple cuts where I take S to be just the single vertex S and T to be the remaining vertices. Moreover, I take T to be the single vertex T and S to be the remaining vertices. Those just say, oh, the capacity out of S is an upper bound on the flow, and the capacity into T is an upper bound on the flow. And this is even more general, okay? So we always have that observation. And then the Ford-Fulkerson theorem, or the max flow min cut theorem, says the best flow we can ever have is equal to the capacity of the smallest cut. So there's finitely many cuts, right? Because there's finitely many partitions, and even fewer of those are cuts, right? A cut is a type of partition where S is an S, T is an T. So among all those, there is a minimum, and that minimum value is the best you can do for a flow, okay? Now, there is actually a question here. Is the term max flow well defined? After we prove the theorem, yes, because min capacity is clear, right? There's finitely many cuts, and each one of those has a capacity. And so just take a minimum one. And I'll say the max flow is equal to that. That proves the theorem. I mean, proves that there's a max flow. But without that, if I just talked about flows, it's not clear there's a maximum flow in the thing, because even though my examples were all integer valued, imagine my capacitors are some real values. And somehow I could have like a sequence that converges, but like doesn't actually achieve the value of like better and better and better improvements to my flow. Like in principle, we could have such a thing that, oh, here's a good flow, but I can add a little epsilon more by shifting things around, and I could do it again and do it again. You can prove directly that's not possible, but here we don't even need to do that thing. If the values are integer valued, then okay, actually even then in principle, you could have an infinite sequence of improved flows, okay? But we don't have to worry about that. We actually just need that there's clearly a minimum flow, minimum capacity, sorry. Okay, so what's the theorem? And the proof is going to be a little rushed here, but okay, Ford-Fulkerson. So it's either called the Ford-Fulkerson theorem or often just called the max flow min cut theorem. Always like a theorem whose name is the literal statement of the theorem, right? Like, so the theorem is in a network. I don't know, we can call it D. The maximum value of a flow is equal to the minimum value of a cut. Okay, so maximum value taken over all flows is equal to the minimum value taken over all cuts. Those two things are equal. Okay. So the proof, I've written out a formal argument in the notes. Here, I want to prove it kind of with a very simple picture and procedure. Okay. So we know that any flow F is bounded above by any cut. Okay. So we're going to say let F be a max valued flow. And we just want to show, and then so find, so this is our goal here, a cut ST such that S capital T, such that the value of the flow is at least the capacity of that cut. Okay. That proves our theorem because we know that this capacity here is always an upper bound on the flow. And so if our max flow is an upper bound on a specific cut, then this is automatically a minimum cut, and the two things are equal to each other, right? This combined with this here. So the goal of the theorem here is starting with the maximum valued flow. So we do need it, right? We do need to prove that a maximum valued flow exists a priori, right? Because we're actually using the existence of it. So this will be an exercise. So that does need to be proved, right? We're talking about a maximum valued flow, and I'm going to construct for you what will be a minimum. If we did it in reverse, which in principle is possible, we could avoid this. Okay. Yeah. I mean, I already have this written out and it's an exercise in the notes, but somehow, you know, it's one of these things when you're going through the proof, you're like, oh, wait a minute, maybe you don't need it. And it's like, no, this thing's been around for 80 years. Like you need it. So anyway. Okay, so the existence of max value flow is not immediate. It's not hard. Let's find a cut that's a lower bound, and then we have equality. Okay, so how do we do this? So I describe a very simple procedure for creating a cut. What I'm going to do is put vertices into S, and then I'm going to check at the end that T didn't end up in S. As long as T didn't end up in S, then I have a cut, and S is an S. And then this procedure will confirm that actually this one satisfied this thing here. Actually, you'll have equality directly from this guy here. Okay. So yeah, if you have equality, then this is automatically a minimum cut anyway, because it's always an upper bound. If you get equality, there's no one smaller than the one with equality. Okay. So we'll define S iterative or recursively as follows. So what I'm going to do is start with S equals just the source. S, okay? So that you put that into S to start with your cut. Obviously, that's what you want to be in there, so we'll just start with it. So that part's guaranteed. Now I'm going to add vertex Y, and this is recursive, so I'm going to repeatedly do this procedure to S if one of the two things hold. If either there exists an X in S, which could be little s itself, such that the flow on XY is strictly less than the capacity on XY. I'll illustrate this in a moment here. Or the flow into X, so back to S, is greater than 0. So let me draw this picture here. So here's S so far, right? So it has little s here and has other vertices there. And I'm looking at a potential Y that I want to add to it. Now I'll draw Y and Y prime because there's two different scenarios for when I would add it. So I would add Y to S if there was an X in here that was directed towards Y and the flow on this arc was less than the capacity. So what does that mean? That means potentially I could bump up the flow there. I mean, at least as far as the capacity rule is concerned, that Kirchhoff's law may not allow me to do that. But if there's available flow on that thing there, otherwise, the other reason I'd add it is if this points in the opposite direction and there's some flow going back into S. Okay. And what does this say? This says, well, potentially I could decrease the flow there and make this scenario better, right? I want to decrease this flow here. So I just repeatedly add vertices like this. So just as an illustration, because that's important, say there's a vertex Z that doesn't get added here. Z wouldn't get added because on every edge pointing from S to Z, the flow equaled the capacity, right? There wasn't room to improve it, or if there was any arc in this direction, the flow on it was 0. Okay, this is, and we'll return to this in a moment. That's what a vertex looks like that can't get added to S. Okay, but just repeatedly do this. Anytime there's a vertex whose flow to that vertex is below C, add it into S, or if you have this. And it's possible, of course, to have both at the same time, right? I could have arcs in both directions, and this one's less than C and this one's greater than 0. Like, that's fine. You just add that one. All you need is one or the other to be satisfied, or both, maybe. So, okay, I don't need either. I just say, like, let's just cross that out. So, yeah, either is a bad word, right? So if there exists an S such that this or this, you know, or both, right? The non-exclusive or like we have in math. Okay, so this produces a partition, but there's a potential problem. This may add T, sync vertex T, to this set S, and then it wouldn't be a cut, right? It could potentially absorb all the vertices, or it could absorb the vertex T. I want a cut that has the vertex S in one class and the vertex T in a different class. So let's actually check, okay, if that happens. So is T in S after we finish this procedure, okay? This procedure clearly terminates because there's a finite number of vertices, right? Eventually it'll stop, okay? So if so, then there exists a sequence of vertices that got T added to the set, right? So like, why was Y added? Because there was an X that satisfied the property. Why was X added? Because there was an X prime that got X added. Eventually, why was T added? Because there was some vertex before it that satisfied one of these rules here, okay? So if there exists a sequence, the following, starts with the source, X, and I'll call X naught, and then we have X1, X2, all the way up to Xk, which equals T. Okay, there's this sequence of vertices that we added such that you have the following property. This looks a little technical, but I'll describe it in the draw picture. Such that there's a value epsilon I, which is the gap between either F and C, or it's the gap between F and 0 if it's a reverse direction edge. Remember, there were two scenarios for when you would add a Y. There was a forward edge that didn't reach the capacity, or a backward edge that had more than 0 as its capacity. Okay. So let's say this is the bigger of the two. So the maximum capacity from xi to xi plus 1 minus the flow, xi plus 1, or f xi plus 1 xi. This is a reverse edge. So if this value, so if one of these values is greater than 0, what does this mean? This means there's a reverse flow that's greater than 0. That's this scenario. And this one means there's a forward flow that doesn't reach the capacity, right? That difference is greater than 0. And if there's two of them, right, a forward flow, there's a gap, or a backward flow that's greater than 0, just let epsilon I be the bigger of the two. That's all. If you have two choices, take the one with the bigger gap. That's all that's saying. Okay, so what does this picture look like? This is saying there's an S here, and then this sequence of vertices reaching T that looks as follows. We have a forward edge here where F is less than C. Say, this is just one example. Say another forward edge here where F is less than C. Then maybe we have a backward edge, and in this one, F should be greater than 0. If you have a backward edge, say another forward edge, F is less than C. Another backward edge, F is greater than 0, and then a forward edge, F is less than C. Okay, so this is one example of this. And each of the gaps between these two numbers is my epsilon I across the whole list there, okay? It's possible these are all oriented forward or all oriented backwards, okay? All right, I want to finish this proof, so just bear with me real quick, but I can basically, I'm almost done here, okay? So this is the scenario if T ends up in S, we have this sequence here. Now here's what I'm gonna do. I'm gonna put epsilon equal to the minimum of across all the epsilon i's. So each of these edges has an associated gap between F and C, right? Some small epsilon. Just choose the smallest of all of those. And I'm going to update my flow as follows. There's a flow on this edge from here to here. I'm going to add to this flow epsilon. Okay, I'm adding epsilon to that flow. It still satisfies the capacity law because epsilon was at most the size of the gap between those two. I'm going to add epsilon here as well. Notice now the capacity law is satisfied at that vertex. More epsilon more in, but epsilon more out. Now reach this vertex here. And here, instead of adding epsilon, I'm going to subtract epsilon. This flows in the wrong direction. Flow is greater than 0. That gap is smaller at most epsilon, so I can decrease it by epsilon safely. And notice, Kirchhoff's law is still satisfied at this vertex because this is plus epsilon in minus epsilon in. So they still sum to 0. The reverse direction allowed that. Then here I add epsilon, subtract epsilon, add epsilon. Okay, clearly the capacity rule was always satisfied, and the Kirchhoff's law was also satisfied at each vertex. What can you tell me about the value of this new flow, though? It increased by epsilon. We just got a better flow. We added epsilon in every single point here. Added or subtracted as appropriate. So the total flow into T, or the total flow out of S, just increased by epsilon. That's a contradiction, right? VF was a maximum flow, and we just made a flow with more. So what this means is that T is not an S, right? That's what we contradicted. Okay. Shoot. All right, let me just get through this real quick then. Okay, so what this means is indeed ST is a cut, indeed. Right? Because the point was T is in T. Right? Oh yeah, so I didn't say T was the remainder of the vertices of the digraph minus S. So we do this procedure to build up S, everything left over is T. T is not in S, so T is in T, which is good. So it is truly a cut, okay? And so now let's compute the value of the flow. So the value of the flow is, say, what do I want to say here? Okay, let me draw a picture and just leave it there. So here's S and here's T. And now let's look at capacities across real quick. Okay, and maybe a reverse edge here too. Now let's think about our rule here. This vertex here was not added to S in the procedure. So that means that the flow on this edge was equal to the capacity of that edge. Otherwise, I would have added to S if it was smaller. So F was equal to C on all these. What about the reverse edge? What's the flow on this edge equal to? Yeah, it has to be 0, otherwise it would have been added. So once we have this picture, we now know that all the forward edges flows equal the capacities, okay? And so that means that the cut value here of ST is actually equal to the flow of F. Why is that? Well, the flows are all equal to the capacities of these guys here, and the total flow is everything into T, right? So here's vertex T. But look at all this flow crossing this cut. Where does it end up? It doesn't get back because F equals 0. Like, it doesn't get back. So all this flow coming in from these edges here eventually terminates in T. It has no choice but to end up in T. And so that's the value of the flow, is exactly equal to that. And it's equal because all the flows equal the capacities there by the definition of that set. Actually, that's the end of the proof. So, I mean, you can write out more words, but that's exactly the argument, that the reverse flows are 0 and the forward flows are C. And that's literally like, yeah, that, and that this is a minimum that was satisfied by the fact that it's always an upper bound. And so this one that equals it had to be the smallest among all cuts. If it was smaller, then it would be, you'd have a contradiction immediately. Okay. All right. So I'm stopping there. Sorry for keeping you guys 5 minutes over, but I wanted to make sure to get through that. Maybe to end with, this also produces an algorithm. Okay. This line up here, you can start from scratch and repeatedly perform this thing. You find a path from S to T and increase or decrease the flow, augmenting it if you can. You do this repeatedly and you will eventually arrive at a maximum flow. You can produce a maximum flow by doing this. There's more to it than this. You have to figure out how many times do you do it, how does it stop, but it actually produces an algorithm as well. Okay.